All right. Hello. April 27th, 8 p.m. on the East Coast here in the USA. We are glad to have Dr. Naresh Osti, the neutron scattering division scientist from Oak Ridge National Laboratory, Oak Ridge, Tennessee, USA. His background is from chemistry with expertise in neutron and X-ray scattering techniques and the characterization of energy-related materials to relate the structure-property relationship. He has interest in exploring the structure and dynamics of new material for the real-life application, especially of the nano-confined fluids, polymers, and polymer nanocomposite. He has wide-ranging experience, including the Oak Ridge Scientist Experiment, experience on the Instrument Scientist as a backscattering silicon spectrometer basis lab, and also he has experience as a postdoc research associated as ORN, and he also has a wide range of experience when he was graduate research assistant at Clemson University, where he did his PhD. And although he's from chemistry background, we are really glad to have him because his background and the work is very closely related to what we have been reading and what we see in physics. He has been awarded by he has received several awards. American Physical Society Gera Travel Award in 2023, Royal Society of Chemistry Faraday Division Horizon Award in 2021, American Physical Society Award again in 2020, and other include Significant Event Award 2017 from the Oak Ridge National Laboratory, and several of those are listed. Without any further ado, we would like to welcome Dr. Naresh Osti. Dr. Osti, the platform is yours. Thank you so much.
Thank you, Nalvinji, for kind introduction. First of all, I'd like to thank ANPA for giving me this opportunity to talk in this colloquium. Today, I'll be talking about the dynamics of the confined fluids, that is water or organic solvent or ionic liquid in material of energy application, particularly using neutron scattering technique. Why neutron? Because it doesn't mean that we have the two big neutron scattering facilities here at Oak Ridge National Lab. We do have the high flux isotope reactor, which is a continuous neutron source, and we also have the accelerator bed neutron source, which is a spallation neutron source. It is not because you have the neutron facility here and then we use the neutron for material characterization. It is because of some of the unique properties of the neutron. Some of them are listed here. If you can see, the very first property of the neutron is neutrons do not have charge with them. That's why they have the very high penetration power. Because of that, we can get the bulk properties of the material. And the another thing is the wavelength associated with the neutron, which is in the order of the atomic length scale. Therefore, it is helpful to resolve the atomic structure in the material. And furthermore, the energy associated with the neutron is in the same of the magnitude of the some sort of the excitation that you think of present in the material and that of the molecular dynamics takes place in the material. Furthermore, the neutrons also have a spin. Because of the presence of the spin, we can use neutron to resolve the magnetic structure and dynamics. And most importantly, the neutron scattering is totally dependent upon the scattering cross-section of the elements. If you look at this table, I have listed some of the elements and their neutron scattering cross-section. If you look at the hydrogen and the deuterium, they have the totally different incoherent neutron scattering cross-section. If you see, the hydrogen has very high incoherent scattering cross-section compared to the deuterium. Using this, contrast on the scattering length density, we can bring the variation in the scattering length density of the material in order to prove the, the system of interest. You can play with the hydrogen and the deuterium to make only one object visible, and you can play with them to make the another object visible. You can also play with them to make the both object visible in the material. It means that it allows you to give you selectively mask a certain portion of the material so that you can get the information from the another portion of the material. That's why this is the unique capability of the neutron, which you do not get in other technique. Therefore, we use this technique to resolve the structure and dynamics in material. Let me briefly introduce how does the technique work, because I think it would be helpful for some of you who may not have the knowledge about the neutron scattering technique. What we do in this technique is that we hit the sample with a neutron of certain incident energy. After interaction with the sample, it gets scattered with making a scattering angle and the scattering vector, which is q, and the scattering angle 2 theta, which is related with this equation. If the scattering event is totally elastic, that means there is no energy exchange between neutron and the scattering domain. At that time, if you plot the scattering intensity as a function of the momentum transfer vector, you end up with something scattering pattern look like this. And the intensity decay profile at the intermediate Q regime becomes the signature of the size or the shape of the particles. Depending upon whether you have the spherical particle or elongated particle, you may end up with a different slope of this intensity decay profile. And at the higher Q regime, where you get the information about the atomic interatomic structure, which we mostly resolve using neutron diffraction technique. And at the low Q regime, which is probing the larger structure, by using small angle neutron scattering or very small angle neutron scattering or ultra small angle neutron scattering, it helps you to resolve the size of the particles as well. On the other hand, if you plot the scattering intensity as a function of energy transfer, in case of the elastic scattering, you will end up with a peak centered at zero energy transfer, which we call the elastic peak. Now, situation would be different when you have the finite energy exchange between neutron and that of the scattering sample. At that time, you will end up with getting the inelastic peak in both the energy gain and the energy loss axis of the spectrum. There is the third situation where the exchange energy is not zero, but very small. At that time, what would happen is that you end up with the broadening of this elastic peak in the cost of the decrease in the intensity of the elastic peak, which we call the quasi-elastic peak. And this, depending upon the width of this peak, you can extract the time scale of the dynamic processes happening in the material. And the shape of this quasi-elastic peak gives you some information about the nature of the dynamic processes happening within the system. This quasi-elastic peak or the quasi-elastic neutron scattering is directly depends upon the incoherent neutron scattering cross-section of the element. As you can see here, the hydrogen has very high incoherent neutron scattering cross-section. Therefore, this technique is highly applicable to resolve the dynamics of the hydrogen-containing material, for example, water or some organic solvent. Here I have listed acetonitrile and ionic liquid, which has the hydrogen only and cation. And in this technique, what we do is that we measure the dynamic structure factor, which is the combination of the elastic component, inelastic component, which gives you the background, and the quasi-elastic component. This quasi-elastic component can be Fourier transform, from which you can get the intermediate scattering function. That intermediate scattering function can also be obtained from molecular dynamic simulation. That means this is the beauty of the technique, where you can connect the experimental approach with that of the theoretical approach. That's why this technique is very powerful to resolving the dynamics of the hydrogen-containing material. Now, once you perform the quasi-elastic neutron scattering, what you do is that, as I said before, you extract the width of that quasi-elastic peak, and then you plot it as a function of the square of the momentum transfer. Depending upon the skew dependence, nature of the skew dependence, you can use a different type of the model function. But at the end of the day, you get the diffusion coefficient of all those dynamic processes. And once you get the diffusion coefficient, you can plot that as a function of the inverse of the temperature, and from which you can extract the activation energy. Now, there is another information that you can obtain from this technique. If your the Q dependence of the half with half maxima is not, if there is no Q dependence, that means if you plot the half with half maxima as a function of Q, you end up with just kind of the flat nature. That means that there is the absence of the long-range translational diffusion of moving species in your system. At that time, you extract the another information, another important parameter, which you call the elastic incoherent structure factor, which is nothing just the ratio of the elastic intensity with that of the overall intensity. If you plot that as a function of the Q, and then depending upon the different type of the model, you can extract the the geometry of that confined motion happening within the materials. That's the another important parameter that you can obtain, and this is the beauty of this technique, where you can get the diffusion coefficient as well as the confinement size and the confinement nature of the confinement. You can get both from this technique. So in order to get those information, you have to have the spectrometer that had the right energy window and the right Q window or Q range. There is the time of flight backscattering spectrometer, which is called the BASIS here at Spallation Neutron Source. Being one of the instrument scientists of this instrument, I'd like to briefly introduce the instrument. And this is the instrument. You can see this is a big tank. And this big tank is the end of the 84-meter long, Newton flight path. Well, it's within the with the combination of the having 3 different chopper system, and then you have the analyzer panel that you can see inside the instrument. We can have the very wide Q range, that is from 0.2 inverse angstrom to all the way to the 4 inverse angstrom. And combination of these will also give you the wide dynamic range, so that you can probe the dynamics that happens from 1 nanosecond to 1 picosecond time scale. Furthermore, we also have the different type of the sample environment available. For example, in case of the temperature, you may go to all the way to the millikelvin temperature to 1700 Kelvin. You can also use the magnetic field if you want to in your material. You can also pressurize your. We have this gas pressure set available, where you can compress the material, the gas using up to 4.8 kilobar pressure. And we are also developing some other pressure capability in the instrument. And besides this, we also have the electric field available. You can, subject the material using electric field, under the voltage. You can measure the dynamics of the sample using electric field. So that's also the sample environment available in our instrument. Now, okay. Now, as I said, mostly our research is focusing on quasi-elastic neutron scattering to look into the dynamics in the energy storage devices, which is very important for the energy storage technology. When you think about the energy storage technology, you can think about the supercapacitor, and supercapacitor are nothing, they are electrical double layer capacitor, which store the energy in the form of static charges at the interface between the electrode and electrolyte. And this supercapacitor has the acts as a bridge between the traditional capacitor that has a high power density but of the low energy density, with that of the rechargeable battery, which has high energy density but of the low power density. But in this community, the challenge is to have the energy storage devices that have high power density and high energy density. How can we achieve this? If you look at this equation, that is the energy, which is the function of the capacitance and that of the voltage. Capacitance is the properties of the electrode material, and the voltage is the properties of the electrolyte material. That's why the people try to use the different type of electrode materials and the different type of electrolyte material. In today's presentation, I'll be focusing on the most of the aqueous electrolytes and some sort of the organic electrolytes and ionic liquid. And the electrode material is mostly would be the magazine. And then our approach would be to look at the interface, the structure and dynamics electrolyte on the surface in contact with the magazine electrode. Now, what are magazine? I'd like to briefly introduce the magazine as well. The magazine is a two-dimensional transition metal carbide or carbon nitride represented by this general formula. And those materials are synthesized from the max phases, where M is the transition metal, A is a group 13-14 element, and X is the carbon or nitrogen or carbon-nitrogen together. When you selectively take the aluminum layer out from these max phases by etching, then you will end up with getting the magazine structure, which is shown here in the SEM images. And depending upon the different type of the etchant, whether you use the hydrofluoric acid of certain concentration or you produce the hydrofluoric acid in situ. And depending upon the nature of the agent that you use, you end up with the magazine with the different morphology and the different properties. The properties of the magazine comes out from the surface targeting group. The example where we have used the Newton total scattering together with the multimodal computer simulation, which shows that the magazine surface is rich with oxygen, hydroxyl group, and the fluoride group. Because of this surface terminal group, this gives the hydrophilicity to the magazine structure, and magazine is conductive by itself. Therefore, this is the unique combination of the conductivity and the hydrophilicity within a material, which is rarely which can rarely be found. Because of this, the magazine allowed to intercalate different types of the metal ions, and also and together with the solvent, water or organic solvents or the ionic liquid in between the layers. Therefore, the magazine has shown the promising behavior to be used in different type of the application, which you can see here. The focus of this talk would be the application of the magazine for the energy storage. Now, when it comes to the energy storage, how can you relate the measurement that you do or the information that you can get from quasi-elastic Newton scattering with that of the energy storage? As I said before, the quasi-elastic Newton scattering signal from which you can extract the width of that signal, and from the width you can get the diffusion coefficient. That diffusion coefficient can be related with the rate handling ability of the device, and the intensity difference that you get at the zero energy transfer, which is coming out from the immobilization of the ions on the surface of the electrode, which you can relate to the capacitance. That's how we can make the connection with the electrochemical performance with that of the information that you get from the quasi-elastic Newton scattering technique. Now, once you have the system, and now I explain about the technique, I'd like to give you some of the science example. I'll be giving you the three different type of the example. The first type of example would be of looking at the water dynamics confined in magazine, and then followed by some sort of the ionic liquid dynamics in bulk and confined in magazine, and then also you do one last example where we have looked into the dynamics of the polymer electrolytes using quasi-elastic Newton scattering technique. Now, this is the very first study where we looked at the dynamics of the water confined in pristine and metal ion intercalated magazine. As you can see in the very left side, this is the XRD pattern where we look at the structure. And as you can see in the pristine magazine, you can see the very broad peak. And once you intercalate the potassium ion between the layer, you can see the shift of the peak position towards the low Q. It means that increasing in the Silet's parameter. And you also see here that the peak in the pristine magazine is broader compared to the very sharp peak that you get after metal ion intercalation. It means that the structure becomes much more homogeneous once you intercalate the metal ion between the magazine, which is well illustrated in these SEM images as well. And that homogeneity in the structure also can reflect it from the slope that you get at the low Q from the small angle Newton scattering technique. Now then we move to the dynamic aspect of this study, and at very first we collect the elastic intensity data as a function of the temperature. As you can see, there is a sharp decrease in the elastic intensity at somewhere around 225 Kelvin, indicating that there is water. We are resolving the water dynamics, and if you see the drop in the intensity is sharp in pristine magazine compared to the metal ion intercalated magazine, indicating that dynamics is already faster in pristine magazine, which is further illustrated by the wings of the quasi-elastic signal that you get here. You see the wings is much broader from the pristine magazine compared to the metal ion intercalated magazine, which is the blue symbol. Now, this is the the representative quasi-elastic Newton scattering spectra, and we use the model function to extract the width of this peak. Now here I'm showing you the half width, half maxima as a function of the square of the momentum transfer. As you can see, those half width, half maxima is increasing at low Q and being flattened at the higher Q, which is the property of the jump type diffusion model. And we use the jump diffusion model from which we extracted the diffusion coefficient. Now look into the diffusion coefficient of the water molecule that is found for the pristine magazine. which is 11.01 times 10 to the power minus 10 meters squared per second, which is just half compared to the bulk value. Now, once you look at the diffusion coefficient of the water in metal ion intercalated magazine, which is already 2 order of magnitude smaller compared to the value that you have obtained for the pristine magazine. It tells us that the water in metal ion intercalated magazine is totally confined in between the layers, but this half decrease in the bulk diffusivity value indicates that the water in pristine magazine is not in between the layers. It might be somewhere in the stack or somewhere in the large voids. That's why we don't see the significant reduction in the water mobility. In order to justify that or prove that, we took an advantage of the MD simulation. Now here is the MD simulation snapshot from which you can extract the C lattice parameter for the magazine without having anything in between the layers. Now, if you look at the C lattice parameter that you obtained for the bare magazine, matches nicely with the C lattice parameter that you obtained from the XRD. It means that in pristine magazine there is nothing in between the layers. That means the diffusivity of the water that you measure is not coming out from the water that resides in between the layers. But once you put the metal ion together with the water molecule, and then you see the C lattice parameter that you obtain is nicely matched with that of the XRD C lattice parameter. It means that once you intercalate the metal ion between the layers, that metal ion takes the water together with it and keep in between the layers. That's why we have a significant reduction in the water diffusivity in metal ion intercalated magazine compared to the pristine magazine. That's what we found in this particular example. Now, before I move to the next example or the other example, I'd just like to point that in this particular study, we have used the magazine synthesized using 48% hydrofluoric acid. This is very important because the concentration of the agent, the type of the agent that you have used, it determines the morphology of this material and giving the different information in terms of the diffusivity or the immobilization of the ion in different type of the electrolyte system that we study. So that's the very important thing to remember. Now, this first part was to look at the long-range translational mobility of the water. We also look at the vibrational dynamics of the water using inelastic neutron scattering technique. Here we use the same 48% hydrofluoric each magazine, but we also look at the vibrational dynamics as a function of the type of the metal ion intercalated between the magazine layer. I'm not going to go in detail, but what we found here is that once you intercalate the metal ion in between the magazine layer, there is a significant reduction in the intensity. If you can see here, this intensity is also almost 3 times reduced. Even on that reduction, you can see still a huge difference in intensity. It means that once you intercalate the metal ion between the layer, it removes significant amount of water from the magazine material. Now, if you look at the other, the intramolecular vibrational mode, for example, a bending mode and a stretching mode, what you can see is that in the pristine magazine, there is a very broad, the peak is very broad. Once you intercalate the metal ion, you see the peak becomes much more narrower. It means that the water molecules becomes much more ordered once you have the metal ion intercalation. And that ordering, the order parameter goes up depending upon the size of the ions, which is well reflected by this radial distribution function calculated from the MD simulation. Now I'm moving to the different type of the magazine, which is synthesized using the lithium chloride dissolved in 10% of the hydrofluoric acid, but we are still looking at the water dynamics. Now, if you see here, I have the elastic intensity profile as a function of temperature for the pristine magazine and magnesium intercalated magazine and potassium intercalated magazine. If you see, the scattering pattern looks like almost like similar, but there is no stakes in the elastic intensity profile, indicating that the water is much more confined in this system. And then we collected the quasi-elastic signal and this is the quadrilateral signal, and analyze the signal as the same way we did for other system, which I already explained it. And from this analysis, we extracted the half width half maxima. And here is the half width half maxima of the point signal as a function of the square of the momentum transfer vector, from which we extracted the diffusion coefficient. Now you look at the diffusion coefficient value of all the three different systems. You see all the diffusion coefficients are in the order of 10 to the minus 12 meters squared per second, even in the pristine magazine. It means that the water in all these three systems are in between the layers now. It is not in this in the stack. They are in between the layers. That's why there is a significant reduction in the water diffusivity. Another thing we found in this particular study is that if you look at the diffusion coefficient of the water from potassium intercalated magazine, it is smaller compared to the diffusion coefficient from the magnesium intercalated magazine, which is quite interesting because the magnesium ions makes the very tight hydrogen, hydrogen shell with the water molecule. So if it makes the very tight hydrogen shell, we would expect the lower diffusion coefficient, but it is not the case. After getting this value, we went back and checked the d-spacing of those samples, and now see d-spacing of the magnesium intercalated magazine is higher compared to the potassium intercalated magazine. Because of that higher d-spacing, water has more freedom to move within that sample compared to the potassium intercalated magazine. That's why we got the higher diffusivity in magnesium intercalated magazine. Now we move to the different magazine, which is titanium carbonitride magazine, and comparing the water diffusivity with that of the pristine magazine. Both magazines are synthesized using 38% hydrofluoric acid. If you see the elastic intensity profile for the carbonitride, there is a kind of the monotonic decrease in the intensity, indicating that there is very less amount of the water, even if present. But in the pristine magazine, you can see the multiple steps. It means that there are the water confined at different regime, but there is a significant amount of the water in the pristine magazine. We collected the Queen's spectra, and the Queen's spectra from the carbonitride magazine could be fitted with a simply delta function. It means that the water in carbonitride magazine is very small, and within the sensitivity of the instrument, that water molecules are not mobile. But the pristine magazine, as before, we got exactly the same type of the behavior, somewhere about half reduction in the water diffusivity in this pristine magazine as well. Now we've done so far. What you did was that we looked at the mobility of the water in magazine powder. Now we move our attention to look at the dynamics of the water in magazine paper. Magazine paper means once you have the magazine layers, you can delaminate the magazine and get a sheet-like structure, and then we look into the water dynamics on those magazine paper and compare the water dynamics with that of the magazine heterostructure. We had the magazine heterostructure, that means to magazine in heterostructure with titanium oxide. What you found is that you see the in case of the pristine paper, the intensity is significantly higher compared to the magazine heterostructure, indicating that there is very high hydrogen containing material. And then we also collected the Queen's signal. We analyzed the Queen's signal and plotted as a function of the square of the momentum transfer. What you see here is that compared to the previous cases, you could see strong Q dependence, but here the water molecules are not, half with half maxima is not showing Q dependence. It is kind of flat. It means that the water molecules in this sample are totally confined. They are not moving within the time scale to the long distance within this sample. That's what we figured out in terms of the magazine papers. Now, I almost finished with the water dynamics thing. Now moving to the ionic liquid system. Now, this is the first example where we look into the dynamics of the ionic liquid in presence of the organic solvents of different dipole moment. This is the bulk solvent, bulk acid, it is in confinement, and the ionic liquid is BBM TFSI, and we have used the different type of the organic solvent with different dipole moment. Now, very first thing we started to look into the potential of the main force required to put the ion apart in the ionic liquid and organic solvent system using MD simulation. We shows that you need the very less amount of these force in order to dissociate the ion pairs when you have the solvent with the high dipole moment. It scales nicely with the dipole moment of the solvent, and we became able to extract the mini square displacement of the ions, from which we have calculated the diffusion coefficient of the cation of the ionic liquid using MD simulation. You can see the strong trend of the increase in the diffusivity as you go higher to the dipole moment of the solvent. This is the MD report. Now we move to the quasi-elastic neutron scattering experiment. What you did here is that I like to remind you, as I said before, this technique, the beauty of this technique is that you can selectively match the information that you get from one component to another component. Here we are using the ionic liquid. The cation has hydrogen, and our solvent is all deuterated solvent. That means whatever signal we get is only getting from the ionic liquid, not from the solvent. Now, this is the representative quasi-elastic signal as a function of the dipole moment. And now in the bottom part, I'm just showing you the concentration dependence of the quasi-elastic signal using acetonitrile as a solvent. We just did the concentration dependence just for only one solvent. Now here in the right side, what I'm showing you here is the dynamic susceptibility as a function of the energy transfer. This dynamic susceptibility is another way of representing the quasi-elastic neutron scattering signal. When you plot the dynamic susceptibility as a function of the energy transfer, by the way, you simply use this expression to translate the SF dynamic structure factor to the dynamic susceptibility, and once you plot it, the number of the peak is a function of the energy transfer that you see. The number of peak corresponds to the number of dynamic processes present in the system, and the peak position, the position of the peak, gives you the time scale of the dynamic processes. If you look at this dynamic susceptibility, you can see the two distinct peaks. One is at low energy transfer, another is at higher energy transfer, indicating that we have the two different type of the dynamics in the system. But if you look at the concentration dependence, there is a significant significant change in the low energy transfer. This blue is coming out from the pure ionic liquid, and others are in presence of the acetonitrile. You can see that this peak position is significantly changing when you change the concentration of the organic solvent. It means that low energy transfer peak is coming out from the ionic liquid rich phase, and then high energy transfer phase, this is coming out from the solvent rich phase, which is the organic solvent rich phase. Therefore, in order to capture the dynamics in those two processes, we use the sum of Lorentzians, two Lorentzians, from which we extracted the half width half maxima. Here is the Q dependence of those half width half maxima. I'm not going to go into detail, but you can see similarly as before, we extract the diffusion coefficient and plotted as a function of the dipole moment. As you can see, this is the slow process. The slow process is always the long-range translational process, which is the very important process. The fast process is coming out from some sort of the in-case rattling motion, but it's not coming out from the long-range translational mobility. But the short long-range translational mobility is coming out from the slow process, which shows the strong dependence with the dipole moment of the solvent. As you can see, higher the dipole moment, higher the diffusivity. And in the similar way, if you increase the concentration of the solvent, you can see the increase in the diffusivity, because the more of the solvent molecule, more it spins the ion pair. That's why the ions have a chance to move freely. That's why you can get the better diffusivity at higher concentration of the organic solvent. So now I'm moving to the confined system. Now we look at we are taking the magazine. Now here the magazine is 10% hydrofluoric acid each magazine. And we also studied this system by exposing the system under D2O vapor. I'll also briefly go over that data, but let's look at the just the confined magazine system. And before doing the confined system, we just collected the elastic intensity as a function of the temperature for the bulk ionic liquid. As you can see, there's a strong decrease, decrease in the intensity, as somewhere around 275 Kelvin. This is because of the freezing melting transition, which you can get as a function of temperature. This is the universal thing that you can see in bulk material, bulk solvent, liquid solvent. Now, you can see once you export the G2 vapor, you can see some small, decrease in the transition because of the presence of some of the water molecule that disrupt some of the hydrogen bonding network present in ionic liquid system. Now, this here is the elastic intensity as a function of temperature for the magazine together with the ionic liquid. As you can see, compared to the bulk case, there, instead of the single step, you can see the two steps in the elastic intensity decrease. You see the first step and the second step. This first step is quite similar with that of the step that you can see here, which is coming out from the bulk liquid. But this step is coming out from some of the ionic liquid that get intercalated in magazine. We stayed in somewhere here in this temperature and collected the quasi-elastic neutron second signal, extracted the weight parameter of that, the signal, plotted as a function of the square of momentum transfer vector, from which we extracted the diffusion coefficient. Now you see the diffusion coefficient that we found for this confined ionic liquid is 0.42 compared to the bulk value of 0.92. If you look into this value, this is roughly the half. If you recall, the water diffusion coefficient that we found for the metal ion intercalated in the pristine magazine case was also the half of the bulk value. And this value gave us an idea that, okay, maybe here in this system also, the ionic liquid is not between the layer because the decrease in the diffusivity is just by half. Then we went to look into the XRD profile. We took the XRD profile of the pristine magazine and that of the metal, the ionic liquid confined magazine, where we found that the despacing, the peak position is exactly in the same place. It means that in this system also, the ionic liquid is not in between the layers. It is between the interstack gap of the magazine that we have seen in our very first example of the pristine magazine water system. Now, once we had the D2 vapor exposed, we see a little bit increase in the diffusivity. It went up from 0.42 to 0.55, which later on with the help of the ambient simulation, we figured it out that once you expose the D2 vapor, the D2 had the more affinity to go and stay with the magazine surface, replacing some of the ions, which you can see here very clearly. That's why the ions with a little bit more faster mobility once you expose the system with D2. That's what we found in this particular example. Now, we tried a lot of different type of the ionic liquid system to look at the electrochemical performance, but at some point we decided to look at the electrochemical performance of the magazine, which is synthesized using the solution of hydrochloric acid and lithium fluoride. That's the mixture we use to ease the magazine, and look at the electrochemical performance of these magazine electrode using lithium TFSI and the three different organic solvent, which is dimethyl sulfoxide, DMSO, acetonitrile, and the propylene carbonate. What we found is that once we have the propylene carbonate, it had the very enhanced, extraordinary pseudo-capacity performance, which is well represented by this red curve. That's what we found. And then we look at the in situ XRD profile and also the help of the MD simulation. It turned out that in this system, during charging, lithium ion gets desolvated from the solvent molecule by itself. That means once you charge it, only the lithium ion gets in between the layers, not the propylene carbonate. So if that's the case, we thought like, okay, if propylene carbonate is not getting in between the layers, that means it should show some sort of the bulk properties. That's why we collected the elastic intensity as a function of the temperature using quasi-elastic scattering technique from the charge and the discharge system, which I have shown here. The scattering pattern exactly looks like the scattering pattern that you would get from the bulk, pure bulk profiling carbonate. That means that yes, it's true that lithium ions, shed its solvent shell once it gets into between the magnesium layer. Getting motivated from this particular example, we decided to see, let's look at to the the electrochemical performance of the magazine using ionic liquid and acetonitrile, some sort of the organic solvent. For this one, we particularly choose the acetonitrile and look into the electrochemical performance and the structural and the dynamic analysis. There is the XRD profile, in situ XRD profile that we got with the magazine electrode using 100% ionic liquid and with different concentration of the organic solvent. That means 25 to 75% acetonitrile. But what we found from the XRD structural characterization is that there is no significant increase in the d-spacing. Once you had the organic solvent in the electrolyte system. We simply found it just two angstrom of the d-spacing increase once you charge the system. This 2 angstrom increase in the d-spacing is not enough to hold the peak cation of the ionic liquid, which is somewhere around 8 angstrom in average diameter. It means that it gives us an idea that maybe ionic liquid is not in between the layers in the system as well. But if you look at the electrochemical performance as a function of the scan rate, at low scan rate, you don't see that much difference as a function of the acetonitrile concentration. But if you look at the higher scan rate, somewhere around 700 millivolt per second, you see the capacitance is higher from once you have that 25% of the acetonitrile in the system. That's what we found here. Then we move to the dynamic aspect and the inelastic neutron scattering aspect. We collected the quasi-elastic neutron scattering signal from the those system in both charge state and discharge state. And as before, we extracted the half with half maxima from both system and from which we extracted the diffusion coefficient. That diffusion coefficient is mostly coming out from the slope of those half with half maxima dependence with the Q. If you can see, the diffusion coefficient is higher once you have the 25% of the acetonitrile in charge state, and the maximum moves to the 50% once you have the discharge state. That's what we found from the points. And we also collected the inelastic neutron scattering spectra for the same system. I'm not going to go in detail, but what you can see here is that the intensity, scattering intensity is higher from all the charge system. As you can see, the intensity is higher from all the charge system. It means that most of the ions get attached to the surface of the electrode once you charge the system. That's what the information we got from inelastic neutron scattering. But the more conclusive information we can get if we plot the normalized diffusion coefficient as a function of the acetonitrile concentration. As you can see, normalized diffusion coefficient is high, so the maximum once you have the 25% of the acetonitrile in the system, and that maximum shift to the 50% once you have the discharge system. What does it mean? That is that there is a particular concentration at which maximum of the ions get attached to the surface of the electrode. That concentration is around 25% in charge state. Now, once you have the discharge system, you don't have the charge on the, you don't have any external perturbation to the system. At that time, you need to have the more of the solvent molecules to dissociate the ion pairs. That's why the maximum shift to the 50%. That's what we got from this particular system. Now, similar type of the maxima for the charge state and the discharge state was obtained if you get the normalized intensity from the inelastic neutron scattering, and same goes for the capacitance. You see, there is always the maximum at particular concentration. That means this concentration is somehow the optimum concentration at which maximum of the ions attached to the surface of the electrode. Now, so far, what we found is that it is very hard to the ionic liquid in between the magazine layers. Most of the cases, magazine layer, the ionic liquids are not getting in between the layers. That's why in this particular system, what we did is that we before using this as an electrode system, we pre-intercalated the gene using alkyl trimethyl ammonium cation. We just pre-intercalate the using this cation. That means we are opening up the space between the magazine layer. But we try to use the alkyl group of the different chain length, started from the C6 to all the way to the C2 valve, which shows the gradual increase in the gradual increase in the D spacing. But if you look at the capacitance, we found the maximum capacitance once you have the this cation with the C2 carbon chain. It means that this is the optimum type of the the cation that increase the ion transfer in between the layers. Once you have the longer chain, that chain after that it hinders the mobility of the ions between the layers. That's why you ended up getting lower capacitance once you have the alkyl chain of this 16 carbon chain. Now, what we did was that now we took the C2 system and compared the the elastic intensity with that of the pristine magazine. You can see the significant higher intensity coming out from the C2 system. It means that it has much of the hydrogen containing species in between the layers. That puts definitely the ionic liquid in between the layers. We took the quasi-elastic signal, and then here is the quasi-elastic signal. As you can see, there is the quite difference in the signal width as well. And as before, we extracted the width of that signal and plotted here as a function of the Q. As you can see, this is we needed to have the two component model here. The first component, which is coming out from some sort of the rotational or the case motion, but the long range translational mobility that we got. So the Q independent, it is kind of flat. It means that once the ionic liquid gets in between the layers, they are not showing in the long range translational mobility in this particular system. That's what we found. Now I'm in the this is the very last slide, and this is one of our recent study where we look into the solvation dynamics in a polymer electrolyte system. The solvation dynamics is very important in a storage system for the charge transport and the reaction rate, and which is mostly governed by the interaction between the ions and that of the solvent molecule. And the solvation dynamics has been studied by by many different spectroscopy technique together with the MD simulation, and it is found that in the aqueous electrolyte system and in the organic electrolyte system, the solvation dynamic is found in the order of the picosecond time scale, or 100 of picosecond or 1 picosecond. That's the range of the solvation dynamic that has been reported so far. But in this particular system, we wanted to look into the solvation dynamics involving lithium TFSI ion and that of the polymer, which is polypentyl malonyl. As you can see, all these polymer has the hydrogen on it. That's why we took a unique capability of the quasi-elastic neutron scattering technique to resolve the dynamics of these, the polymer in presence of the salt of the different concentration. As you can see, we use from no salt concentration to all the way to the 0.1 concentration. Those concentration are the R is the ratio of the the lithium contacting with the number of the oxygen atom present in the monomer of this polymer. And now we collected the quasi-elastic signal. As you can see here, those are the quasi-elastic signal as a function of the salt concentration. As you can see, the weight is going down as you go higher to the concentration, indicating that salt has significantly reduced the dynamics of the polymer at higher concentration. Now, another beauty of this technique is you can do the Fourier transformation of this dynamic structure factor and plot as a function of the time. This is the spectra, as you can see here. This is from the no salt, and then as a function of the salt. And at no salt and as a function of the salt up to 0.02, you see there is a kind of simple type of the decay. But once the salt concentration is higher than 0.04, you see the pattern looks totally different compared to the pattern that you have observed in low salt concentration and no salt concentration. Now we feed this data using this expression from which you extracted the mean square displacement of those particular system, and from which you can extract the Rouse parameter, which is given by this expression. It is nothing just like the normalized mean square displacement with the square root of the time, and we are plotting this as a function of the temperature. What you can see here is that at higher, lower low salt concentration and higher, and the concentration up to 0.2 concentration is shows the some sort of the natural type of the Rouse parameter. But at higher concentration, you can start to see the decrease in the Rouse parameter, and then start to form a plateau. That plateau is coming out from the formation of the solvation shell between the lithium ion and that of the oxygen atom of the same monomer of the same polymer, or that of the monomer of the different polymer. And you can see this plateau is there, and after some time it starts to increase in the Rouse parameter. That means the solvation shell starts to break up. We also obtain the same Rouse parameter using ME simulation. The ME simulation has helped us to resolve what is the time scale of that solvation shell breakout, which is found to be 1 nanosecond, which is the ultra slow solvation shell breakup time reported so far. That's why this research has been highlighted in many different type of the news outlet, including DOE headline news as well. With this, I would like to summarize my talk. I think I became able to convince you that dynamics of the confined fluids in magazine depend on their morphology, and quasi-elastic neutron scattering is a powerful technique to resolve the microscopic dynamics of the different type of the fluids, either in the confined state or in the bulky state, and also helps to explore the mechanism of the electrochemical performance that you obtain for the supercapacitor. And Quench is a technique that can be used to resolve the solvation cell dynamic involving polymer electrolytes. Obviously, basis, that means backscattering silicon spectrometer is a new generation spectrometer to perform quasi-elastic neutron scattering technique. With this, if you want to use the neutron scattering technique in your research, not only the basis, any type of the neutron scattering technique, we are always ready to discuss with you and with your system, and then help you out to figure out which technique is suitable to resolve the dynamics. Feel free to contact any one of us. That means we are always happy to collaborate. And either you are working in the protein dynamic system or the polymer dynamic system, even if you are working in the confined system, if you are working in the confined system where you are looking at the ion dynamics, as well as even if you are working in the hard condensed matter, we are always happy to collaborate with you and then guide you to the right person if your subject area is not falls within our expertise. With this, I like to acknowledge the funding, mostly the first center. Many of the work that I have presented is the work that I did during my postdoctoral position here. And then the funding was from the first center. And I was fortunate enough to have to work with a lot of different renowned groups from different national lab and the universities. With this, thank you for your attention. I'll be happy to answer any question that you may have, and happy New Year 2081 to all of you. Thank you.
Awesome. Thank you so much, Dr. Osti. This is completely new topic to me because I'm not from the material science background, but I feel like I learned something or I realized some important topics here where the fluids in confinements, how you can probe it using the quasi-static, I'm sorry,
Quasi-elastic neutron scattering.
Elastic neutron scattering, QENS. So I was reading your abstract, and it's quite fascinating. Where we start, as a basic physicist is like a capacitance C equals to epsilon naught A over D, and then we insert the dielectric. We start like that, right? And then now I'm realizing how much details goes in there to basically probe the nature of the interaction and material that you have inserted in between for robust energy storage solution. That's quite impressive. Thank you so much. So with that, we have a lot of interesting listeners here. Dr. Ambadat Panta, there is our Prakash Nepal, and if anybody has questions, please feel free to unmute yourself, please.
So Naresh sir.
Yes.
I'm Prakash Nepal from Northeastern University.
Yes.
So I would like to go to your neutron scattering, that experimental device where you said your low angle either start from 0.2 or 0.4.
Not the 0.4. It is the maximum is 4 inverse angstrom and the minimum is 0.2.
Yeah, okay, let's consider 0.2. And then so after few slide, while you are showing the power law, you have gone even small angle than 0.2.
No, I think that's okay. So I think I know what you are talking about.
Go to your power law
Here.
slide.
Yeah. This is the small angle neutron scattering, not the quasi-elastic. This is the data collected from the small angle neutron scattering instrument, not from my instrument. Our instrument only resolve the dynamics. This is the structural resolving instrument, which are small angle neutron scattering instrument. It is totally, they have the different detector system. It works totally in different principle. It is not the same instrument.
Okay.
Thank you for getting that. Yeah, I should have. It is the small angle. Yes, I pointed here. This is the small angle neutron scattering data, not the quasi-elastic.
Okay, that makes sense. And
Yeah.
then let's discuss about this power law.
Yeah.
So I see your slope is varying like 2, 3. So in the small angle range, do you have some depending upon your samples, your slope vary, I know. So do you have some range like from 2 to 4 or 2 to 3, 3 to 4 or
Yeah. I didn't put that in detail here because the small angle neutron scattering is, I have done a lot of small angle neutron scattering, but I haven't, nowadays is not putting that in my slide. You are absolutely right. There is the slope changes from the 1, 2, 3, 4. Depending upon the slope, you can think about if you have the scattering profile decay with the slope of the 4, -4, that means you have a totally spherical subject with a smooth surface.
So I know
And
you
then
have
once you have
different
the slope of
samples.
the 3, it means that you don't have the spherical surface, but it has the rough surface. That's why your slope is 3. And then if you have totally cylindrical object, the slope decay would be -1. There is a lot of
That is even like for a regular shape object, but here you are getting some fractal type of
that's true.
fractal, let's say fractal dimension. So
Yes.
within that small range, suppose if you are only focusing on your small angle, that neutron data, let's say within 0.01. Okay, here do you have you, I know you are not showing here, but have you ever realized or have you ever remembered that what would be the variation between minimum and maximum? I know it depending upon sample it change, but normally I know you can think of between maybe 2 and 3 or
The one of the thing is for the small angle neutron scattering, you cannot stay in the particular queue and then collect the data. Okay, so it is kind of you have to have certain Q range, and then that's the ensemble average.
that I understand.
Yeah, you have to have the certain Q range, and then depending on that Q range and then slope or the intensity profile decay would give you some sort of the shape and the size information. But I might have forgotten long because it is not my expertise right now. But what the only thing I can tell you is that the slope becomes the signature of the particle shape and the size.
Even if it is irregular, it can reveal that. So
Yes,
we
you
can
can.
talk about.
There are a lot of, the model goes in. Once you have this is just the model lays interpretation. I haven't extracted the exact parameter because the small angle neutron scattering is not the big part of this research. But what you did was, it is just the model less information that you can get. You see, I of Q is proportional with the Q power minus alpha. It is just like it's just a Porod approximation we use at that particular Q regime, just to get an idea about what type of the material, shape of the material, whether it gives us some sort of the information regarding the homogeneity or inhomogeneity in the material or not. That's what we did. But this is just totally the model-less interpretation.
But seems like you are getting or your samples are mostly inhomogeneous here. Yeah.
Yes. That's
Yes.
what you look into the ACM image. It does tells that, isn't it?
Okay. Yeah. And then another last question.
Mm.
So we can talk about this later also. But at one time, in the water dynamics, you said that there is a void formation. I particularly remember that word, void formation.
No, I didn't say the void formation. Maybe I said it void formation. We are getting the right slide right now. Right now, the void that I mean by, you see the gap between this. Can you see the crusher here? Let me
Yeah.
see.
Yeah.
You see the gap. This gap. This is the void. This is the interstack gap. That's the gap we were talking about. The void means the water. If the water is trapped in this
Yeah.
void, and those water do not feel any sort of the tight confinement. It's a kind of
Yeah.
loose confinement,
Yeah.
and
Yeah.
that's why the diffusivity is larger. That's what I
Yeah.
think I
Yeah.
told.
Yeah. That makes sense, and that may be attributing your power law here also.
Yeah.
Okay.
Yes.
So
Yes.
and how means by only seeing from your eye or from other imaging technique, you are saying, okay, there are significant amount of voids, or is there any other way to confirm the void's presence?
Yeah, here is, to be honest, we simply, I just counted the number of the voids and tried to measure the dimension. That's what we did. I don't know, there is a specific way to find out the number of voids, but might be if you can do some sort of the gas loading, nitrogen, or some sort of glass, the way we define the polydispersity, in the
Yeah. Yeah.
in the pore size
Yes.
determination. I
Yes.
think we could do that, but for this study, we didn't do that.
Okay. Okay. So yeah, and your energy conversion and energy storage talk are also very, very useful. So it's really useful to me. Thank you so much.
Thank you. Yeah, just reach out to me if you need any further
Yeah. Yeah.
information, or you might
Yeah.
have any other question. Feel free to reach out to me at any time. I'll be
Yeah.
more than
Sure.
happy to help you out.
Sure thing. Thank you
All
so
right.
much.
All right.
Awesome. Are there any other questions from the audience? So there is one in the chat. Suresh Kemali has asked, "Great talk, Naresh sir. Are there any open postdoc position in theoretical and computational?" Okay, so you can read that one, and then I think we can discuss that after the formal part.
Okay, that's fine. Yeah, yeah, those who are interested on having some sort of the job opportunity in the Workplace National Lab, feel free to reach out to me, and as much information as I have, I'm happy to share with you guys. And then at the same time, the best source of information would be to look at the career web page of the Workplace, and they always post that job position every day. They update that job position every day. And if you find something relevant to you, and just reach out to me. And if I think I can be of any help, I'm happy to help.
Awesome. Are there any questions related to the talk? If there are, again, thank you, Dr. Osti. It was really interesting talk. I
Thank you
feel
so
like I
much.
learned, yeah, I learned a new topic today. And
Thank you so much.
with this, we're gonna stay here for a few minutes in the informal mode. I'm gonna stop the recording, okay?
Sure.
Okay. So, and then we can have, some discussions.